Good evening, everyone. Today is the 8th week of fluid flow operations live session. So, in this class today, we'll talk about mostly the drag force and drag pressure calculation, lift, and cavitation. Okay, let's start. We'll first go through the sir's notes, and then we will come back to the derivation part little bit, and we'll then solve the equations or problems for this week assignment. Okay, let's start. I think my screen is visible, right? Okay. Come after 9:30. Okay. Sorry. Yeah, yeah. So we will be talking about drag when flow around the body. That means suppose there is a particle inside a flow, right? So if you can think of, like, suppose a pipe flow is happening, right? A pipe flow is happening and there is a obstruction. Suppose there is a particle of a random kind of shape. Okay. Now how this flow, what is coming from left side, how this flow will behave, right? So that is the discussion of today. So this fluid or this fluid can be of different viscosity, different density. It can be like water, like Newtonian fluid. It can be non-Newtonian fluid like paste, right? Sand, right? It can be highly viscous fluids like honey. Okay. And this shape can also be changed. It can be purely sphere. It can be square or some kind of cube, right? Some kind of platen type of thing, sometimes it is can be a rod. Okay, so this is different. So for this different cases, the flow velocity patterns will be different, right? As you can understand. So we'll discuss this type of uh, study in this session. Okay. So first it is showing that flow around the body placed in a uniform flow develops a thin layer along the body surface with largely changing velocities. That is boundary layer due to the viscosity of the fluid. We have learned about the boundary layer, right? So what happens when the flow is this, a particle is there of spherical shape and flow is coming. So it creates a liquid thin layer along, and the surrounding of this particle or surrounding of this your obstruction, and it is happening because there is a viscosity is coming because of this obstruction and there is this boundary, right? So what happens here, the velocity is not achieving the fully developed flow velocity, right? That is why this kind of flow is happening. There is an obstruction. Now furthermore, the flow separates behind the body, discharging a wake with eddies. This is, so you can see here the flow is streamlined, right? In the left side of the obstruction, the flow is streamlined. But in the right side, there is a chaotic motion. Why this is happening? Because an obstruction is happening, right? You can see in real life, if you imagine, suppose a river is flowing, and in the middle of the river, if it's a big stone, right? You have seen by yourself that how the flow pattern changes around the stone or in the downstream of the stone, right? Especially you can see these things in hilly area rivers, right? So you can have seen that how the water creates a turbulent motion or chaotic motion around that particle in the downstream direction, not in the upstream direction, right? So this is all about this flow around the body. Flows around the cylinder. We will talk about this in a little bit later. Like I am going through the overall view that what is going, sir has taught in this session. Then I will come to this individually, okay, with required derivation, okay, or some calculation. Okay. So we can see that flows around the cylinder and a flat plate shown different figure. Okay. So what happens? The flow from an upstream point A, this is point A, is stopped at point B. This is because this flow cannot go anywhere. The surrounding streamlines can cross this cylindrical obstruction, but this particular streamline cannot cross, right? So it is a point at it is stopped at point B on the body surface with its velocity decreasing at to zero because it is going nowhere. It is like stuck there. That is why velocity is going to be zero at this point. Okay. This point is called stagnation point because there is no pressure. The flow divides into the upper and lower flows at point B. You can see, right? So for a cylinder, the flow separates at point C, producing a wake of weak eddies. So you can see here, flow is separated. In this case, flow is separated at B point, but it's for this case, for the cylinder, flow is separated at point C. Okay, you can see and how the pattern changes, and this creates a chaotic motion. We'll come to that. So here it is same written that let upstream pressure, suppose this pressure at this stagnation point it is P naught, and pressure A not affected by the body is P infinity, right? Here it is P infinity, here it is P naught. So what it is happening, if you remember the Bernoulli's equation, you can see that here there at this point there is no velocity, so it is only P naught equals to this is P infinity plus rho u square by 2. Right? So now realization of drag and lift. So what is happening? So a body realizes a force from the surrounding fluid whenever it is placed in a flow of fluid. A flat plate realizes a force only in the downstream direction, right? When it is placed in the flow direction. However, a wing realizes the force R inclined to the flow as shown in figure. So suppose there is a body, you can see there. So the resultant force is acting in this. So it has two components along with the flow, that is D, drag, and along the perpendicular of the flow direction, that is called L. So it is written here that in general the force R acting on a body is resolved into two components, D in the flow direction of velocity referred to as drag, and if the component L in the direction normal to the U is referred to as lift. Okay. So now you have seen that the now what will be the force along the those, so this is the area, right? dA is called the area. So along the where the flow is like where the force is applying is called the dA area, right? So here you see that the drag dP here, right? Where this is the flow along the force component drag along the flow direction, which is defined as dP, which is the integration over the whole body surface of the component in the direction of the flow u of this force PdA, right? So suppose there is a flow. What is there? Yes. Suppose there is a particle and that is a small area, and area is along this dA, right? And this is this is the flow along this, and this is the flow is perpendicular to this. Right? This is the perpendicular direction. Perpendicular along the perpendicular direction. This is dP, and this is leaf direction. Okay. So you can see that the drag dP, which is integration over the whole body surface of the component in the direction of the flow velocity u of this force PdA. So here the force is applying. So you know that this is here this is area dA, and here then the perpendicular direction the force is applied as PdA, right? So this is, if this is theta, so dP is equals to PdA cos theta component, right? Right. Now what is the drag dF is a similar integration of tau dA and is called the friction drag. So friction is happening. So here this is the dF. Here this is the friction drag component. It is the tau d cos theta, right? And it will be integrated. So one is in the perpendicular direction and one is at the tangential direction. Okay. So tangential directional force is taken care of by stress. This tau is stress, and this is the normal pressure. Okay. Stress means shear stress. So the drag D on a body is the sum of the pressure drag dP and friction drag dF, whose proportions vary with the shape of the body, right? So for different shapes, how this pressure drag percentage and friction as percentage are varying, you can see here. So from the previous classes, you have seen the drag force component, right? So drag force is nothing but the CdA rho u square by T. A is the projected area of the body on the plane vertical to the direction of the uniform flow, and CD is a non-dimensional number called the drag coefficient. We have derived all this. We have derived the drag coefficient. We have seen how drag coefficient is varying for laminar flow to turbulent flow. There is some a little derivation about how this is coming. We will do that, but let's first go through the notes. So this is for different shapes of body and how they are presenting at the flow direction. So when the cylinder is in horizontal position. So the projected area is pi by 4 d square. Okay. When the cylinder is in the vertical position, the projected area at the vertical plane is dl, right? And this will also change with the dimension ratio, and that is how the drag coefficient also change. Okay. So here a long board, you can see here this is the projected area is A cross B. See, for hemisphere, same. The projected area is this, the like pi by 4 d square. That means only the area, only the bottom area of the hemisphere. For cone also this. So you have to think about that. Now comes the drag for a cylinder particle. It is considered a cylinder placed in a non-viscous ideal fluid. The flow around the cylinder placed at right angles to the flow u of an ideal fluid. Okay. So the velocity component v theta, you can see here the v theta at a given point P on the cylinder surface is as follows. Okay. Vu 2u sine theta. Applying Bernoulli's equation. Now we are applying Bernoulli's equation at this point P and this point. Okay. Bernoulli's equation, I am substituting the pressure of the parallel flow as P infinity and the pressure at a given point on the cylinder surface as P. So P infinity, the velocity of the fluid is at its optimum one, like the fully developed flow velocity. So it is rho P infinity rho u square by 2, and then comes the at the edge of the particle. So it is rho with v theta square by 2. Now you can put the values of this, and this is coming like this. Okay. So this is the ratio for different RE, how this value is changing in this case. Okay, so for pressure and friction drag, we have seen the component along with the flow, right? In the direction of the flow, how the drag is occurring for normal pressure and for tangential pressure, that they are called pressure drag and friction drag. Now for the lift case. Okay, so in the same diagram, if you consider the perpendicular component of the PDA force. So for PDA force, perpendicular component will be this, right? So it will be LP, and for this tangential part, this will be this will be LF. So similarly, there they will account for the LP is the pressure lift component, which is the PDA sine theta, and LF is the friction lift component, which is the tau dA cos theta. Okay. Okay. So I think the previous case, this is sine theta. Yes, the stress, this is like dF is tau dA sine theta. Sorry for the mistake, please correct it. Okay. And for LP, it is P dA cos theta, and LF, it is tau LP sine theta, and this tau dA cos theta. Because this angle is theta, right? So this is 90 minus theta, and this is again theta, right? Sorry for the mistake, please correct it. So they're showing that drag for a cylinder when the Reynolds number is very low, less than 1, how it is looking like. I will come to that again in a better way, with better explanation. Right now, you just see this. So now when the Reynolds number is varying between 2 to 3, you can see that the chaotic motion started coming, right? So these chaotic motions are called eddies. So now you can see the Reynolds number regime is a little bit higher zone, like between 40 to 70. So it is the periodic oscillation of the wake is resulted. So you can see a twin vortices. You can see this, right? This is the twin vortices. Now it is greater than 90. So now you can see that these eddies are not coherent. So they are creating a random kind of motion. The eddies are continuously shed alternately from the two sides of the cylinder. So you can see now the range is even higher, between 10 square to 10 to the power 5. So the separation happens at this position, and you can see how this pattern is coming, right? It will create a alternate motion if you see in a video mode, right? So now it is even higher. So the boundary layer becomes turbulent. Okay, now the boundary layer itself becomes turbulent because the Reynolds number is very high. The fluid is flowing at very high speed. The boundary layer becomes turbulent. The separation position is moved farther downstream, right? So now it is 130 degree. So earlier it is happening at this position. Now it is happening at this position, 130 degree. From the front stagnation point. Stagnation point is this zone. Right? For the rear half of the cylinder, just like the case of a divergent pipe, the flow gradually decelerates with the velocity gradient reaching zero. This point is called the separation point. So you can see this is the separation point where the downstream flow gets reversals. Here, that means the downstream flow is want to come back because the flow speed is very high and developing eddies. The fluid particle in and around the boundary layer mix with each other by the mixing action of the turbulent flow. So see, so this frequency can be represented by this number n. The number of vortices separating from the body every second for this particular Reynolds number fluid can be obtained by this equation. Okay, it is a classic GI Taylor equation. You can remember this because problem may come. How you can see here. So what is streamline shape? Most of the contribution to produce drag is due to the separation of stream behind a body, right? Which develops vortices and lowers its pressure. Therefore, in order to reduce the drag, it suffices to make the body into a shape from which the flow does not separate. So if you make your, like, if you have two kind of two shapes. So flow is happening here and flow is happening in this case. Where do you think the flow will separate first, or flow will separate at all? So in this case, the flow separation will happen, right? But in this case, it will not happen because their object is so much streamlined, so they will not let the fluid create some chaotic motion. Okay, so how this drag coefficients for cylinders and other column-shaped bodies are varying. You can see from this chart, and you have to use this chart for calculating the CD with respect to I. Right? So we have earlier defined that at the Stokes equation, the drag coefficient for laminar flow can be is 24 by RE. Okay, and for different shapes, modification of Stokes equation by Osin, partly taking account of the inertia terms. So now the empirical equations comes and this drag coefficient formula is changing a little bit over time. Okay, you can see. So drag coefficient of a sphere. So within the range of where RE is fairly high, right? In this range, the resistance is proportional to the square of the velocity, right? And CD is approx 0.44. You can, if you calculate this, it is approx 0.44. As RE reaches stage 3 into 10 to the power 5 or so, the boundary layer changes from laminar flow separation to turbulent flow separation, as you can see. So CD decreases to 0.1. So drag coefficient is that time very less. On reaching the higher RE, CD gradually approaches to 0.2, right? It again starts increasing. So there are some problems around that. Okay. So over a flat plate, you have seen the for laminar boundary layer. This is the drag coefficient, right? Friction drag coefficient. Drag coefficient formula from where you can calculate the friction coefficient. I will come to that. First, see this for turbulent layer. This is little bit different. The value changes. I will come to the derivation. Don't worry. This is some. Okay. And in the next case, it is about the lift, drag, lift, and cavitation. So you have learned about the drag and lift. Almost you have understood how this is happening, right? So this part is known. So it is repeat one. This is the lift part, and how for every component. For normal force, there are two parts: drag, pressure drag, and pressure lift. And for the shear tangential force, stress force, there are two parts. That is the friction drag and friction lift, right? So now this is known, like at v theta we have calculated is at 2u sin theta. The tangential velocity at v theta at tangential velocity at point P will be Vp equals to v theta plus u, right? U is the rotational velocity of a circulatory body. If the cylinder surface moves at a circular velocity u, suppose along with the flow, the body is also rotating itself. So what will happen? This p velocity will change to v theta will be changing to v theta plus u. So this is how the rotational velocity term will be added. So now if you apply Bernoulli's equation at point A at point P, so this is how the equation will change. The circulation around the cylinder surface tau will be 2 pi r0 into u and lift will be rho u tau. This lift is the reason why a baseball, tennis ball or golf ball curves or slices its spin. Like this equation is called the Tajorski equation. So wing, aerofoil or blade. If the body is so manufactured as to make the lift larger than the drag, so you can see here, right? Here the normal pressure area is very less. There is no normal pressure drag or pressure lift drag, right? Like normal, in the normal direction, the area is very less. So it is it is mostly controlled by the lift larger than. So it is written that lift is larger than the drag. It is called wing or aerofoil or blade. So if you remember what it looks like an aeroplane also, right? So in case aeroplane also, when it flies, the lift force is higher operating at the compared to the drag force, which is perpendicular to the flow motion. So the shape of a wing section is called the aerofoil section. The line connecting the lead leading edge with the this line. Trailing edge is called the chord. So this is your chord. Okay. And its length is called the chord length. The line connecting the midpoints of the upper and lower faces of the aerofoil section is called the camber line. This is the camber line. The height of the camber line, so you can imagine how the wings are being made. It is all about fluid mechanics, right? You understood that how much fluid mechanics or fluid dynamics learning is important in our life, because everything is based on that, right? The aeroplane jet you fly every time, you'll understand. If you remember this, if you correlate these things, what you are learning in this course, you correlate these things with your real life knowledge or real life understanding, real life object, you will more enjoy this subject, right? The thickness of wing as measured vertically. So this is the vertical thickness to the camber or chord is called the thickness. Okay, this line. The angle alpha between the chord and the flow direction u is called the angle of attack. You can see here the angle of attack. If wing width is b, okay, wing width is b and the maximum projection area of the wing is a, then b square by a is called the aspect ratio. Okay. Then if the length of the chord is L for an oblong wing, the aspect ratio becomes b square by a equals to b by L, because a equals to b into L. If the lift tail drag d and moment about the wing leading edge or the point on the chord 1/4 from the leading edge acting on the wing are expressed respectively. So this is the expression. This is the lift force, this is the drag force. This is the moment. So the coefficients CL, CD and CM are called the lift coefficient, drag coefficient and moment coefficient, which are determined by the aerofoil section, right? Mach number and Reynolds number. The wing characteristic is indicated by the values of CL, CD and CM for the angle of attack alpha. So now you can see the zero lift angle. That means the lift coefficient, that is the CL, reaches to zero at a certain angle of attack alpha, which is called the zero lift angle. As the angle of attack increases from the zero lift angle, the lift coefficient CL increases in a straight into a maximum value. So you can see how CL is increasing. The drag is decreasing and again increasing, and also the momentum coefficient is decreasing. So what is showing that if the angle of attack, that is alpha, further increases with increase in CL, gradually slows down, reaches a maximum value due to the flow separates in the upper surface of the wing by high value of angle of attack. This phenomena is called stall. So you can see. So here the angle of attack is going high. What was that? What was the angle? This one, right? So the angle of attack is very high now, right? This alpha is very high at this position. So you can see the flow separation happens. Here in this region, the fluid is not reaching. The flow separation happens. That means again the lift coefficient start decreasing, right? Angle alpha at which CL reaches the maximum is the stalling angle, and the maximum value of CL is the maximum lift coefficient. right? So it is very easy to understand if you think the real scenario in your head. So characteristic curve of a wing or leaf drag curve. A wing characteristic is shown in figure by putting CD on this portion and CL on the ordinate, and is called the leaf drag polar, from which the angle of attack maximizing the leaf drag ratio can be found. So here you can see how the ratio is changing. It is from -9 to -30 at this point, CL, and so this is the angle of attack, right? And this is the ratio of it, CL by CD. So angle of attack is negative, then it is when it is negative, the CL and CD both are in negative, then it starts increasing, increasing, increasing. CL is also increasing. Drag coefficient is increasing at very slow rate, and after some at max reaching maxima, CL is again going down. So here you can see why a wing produces a lift. This is because a circulatory flow is produced just like for a rotating cylinder. So here you can see how the lift is helping. In this case, a wing section, the circulatory flow is produced because the trailing edge is sharpened, right? Here the edge is sharpened. A wing moves from a stationary state initially, right? Owing to its behavior as potential flow, a real stagnation point occurs at point A. So as the alpha is increasing, this stagnation point at point A, the stagnation occurs. Consequently, the flow develops into a flow running around the trailing edge B, right? So flow here the stagnation happens at the top portion, but at the bottom portion the flow starts happening. Float starts happening. Okay. Since the trailing edge is sharp, however, the flow is unable to run around. Since the trailing edge is sharp, the flow is unable to run around the wing surface, but separates from it, producing a vortex. You can see how the vortex is, because at this point there is nothing, no flow, there is complete separation at this A point, but here due to the sharp edge it is creating unable to run around, and it is creating a vortex. This vortex moves backwards, being driven by the main flow. The flow on the upper surface of the wing is drawn towards the trailing edge, which itself develops into a stagnation point. You remember the A point. As one vortex is produced, another vortex of equal strength is also produced, since the flow system as a whole should be in a net non-rotatory motion, right? At the B position, if you remember. Therefore, a circulation is produced against the startup vortex, as if another vortex of equal strength is counter-rotation had developed, because if one vortex is generated, another vortex of strength has to be generated to make it a non to keep the flow in a non-rotatory movement, right? The net movement should be non-rotatory. So if if a vortex is generated from the clockwise, then an anti-clockwise flow will definitely generate it. Anti-clockwise vortex. The former vortex is called a starting a vortex because it is left at the starting point. The latter assumed vortex is a wing-bound vortex. The situation where the flow runs off the sharp trailing edge of a wing, as stated above, is called the Kutta condition or Joukowsky hypothesis. Okay, I hope you understand. So now what is cascade? If this kind of wings are there simultaneously, the blades of a blower, compressor, water wheel, steam turbine or gas turbine. If you have seen these things, you will relate more of the axial flow type are distributed radially in planes around the shaft, and the blade sections of the same shape around same shape are found arranged at a certain spacing as shown in figure. This is called cascade. The action of a cascade is to change the flow direction with small loss by using the necessary stagger angle. So you can see, right? So what are this U1 and U2 here? Velocities at infinity in front and behind the cascade. Alpha 1 is the inlet angle of velocity U1 to axial direction. Alpha 2 is the exit angle of velocity U2 to axial direction. L is the chord length. This is the chord length. T is the space between the blades. L by T is the solidity. Beta is the stagger angle. Theta equals to alpha 1 minus alpha 2 turning angle flow. And turning angle of flow. So now comes the lift acting on the blade is, we have earlier known that the lift acting on the blade is defined by rho v tau, right? Where u infinity represents the mean flow velocity of u1 and u2. Tau is the circulation, right? The circulation around a blade in a cascade is affected by the other blades, giving less lift compared with a solitary blade, right? For the same blade section, setting the lifts of a solitary blade and a cascade blade to L0 and L respectively. So K is this ratio L by L0 is called the interference coefficient. It is a function of L by T and beta, and it is near 1 whenever L by T is 0.5 or less. So now comes the cavitation. When the cavitation happens, if a section of the body placed in liquid and if the local pressure is decreased to the vapor pressure or saturation pressure of liquid, the liquid instantaneously boils, producing bubbles with cavities. This can happen when liquid flows through valves, elbows, or turbine blades when the pressure becomes sufficiently low. This phenomenon is called the cavitation. Right? So why this happens? Because V becomes very okay. Now, since gas dissolves in liquid in proportion to the pressure, Henry's law, right? As the liquid pressure decreases, the dissolved gas separates from the liquid into bubbles, even before the saturation pressure is reached. When these bubbles are conveyed downstream, where the pressure is higher, they are suddenly squeezed and abnormally high pressure develop. At this point, noise and vibration occur, eroding the neighboring surface and leaving on it holes small in diameter but relatively deep. So, if you see some example what it is looks like, so it will be better. See. Okay, so here flow is going, right? Fluid is going and vacuum is increased. That means pressure is very low. So bubble is forming at the edge. Bubble is forming at the edge, and after some times, when it is reaching a higher pressure zone, they are squeezed and vacuum bubble collapse. They are collapsing and damaging this surface. So now they are squeezed. In this case, you can see. So when the area is area is small, the pressure is reduced, right? Area is okay, so it is a convergent type of flow. Here, the pressure drop happens, and because of the very low pressure zone area, this cavitation bubble starts coming, and bubbles become larger, 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 and when it again reaches a high pressure zone, it bursts, releasing the intense energy, and that corrodes the surrounding wall. What it is there? See, it is the pressure drop is happening at this position. At this position, the pressure is very low. Okay. The blades of a pump or a water wheel or the propeller of a boat are sometimes destroyed by such phenomena. They can develop on liquid carrying pipelines or on hydraulic devices in which a contraction and expansion exists in the vanes of a centrifugal pump near the tips of propellers on hydrofoils and torpedoes. It can actually damage the propellers and the steel shafts due to vibrations on ships and cause a pump to cease to function properly. See. So, what is supercavitation? When an aerofoil, so this is your aerofoil, right? Section is placed in a flow of liquid, the pressure distribution on its surface is shown. So, as the cavity grows, here the cavity grows is happening, right? As the cavity grows, the upper pressure characteristic curve lowers, while vibration etc. grow. When the liquid pressure is low and the flow velocity is large, the cavity grows further, right? When it grows beyond twice the chord length, the flow stabilizes with the reduction of noise and vibration. This situation is called supercavitation. Yes. So rocket propulsion can be used for sustained operation with the possibility of tapping high pressure gas to route to the object's nose in order to enhance the cavitation bubble. An example of rocket propulsion is the Russian torpedo. Okay, so you will go through these examples. Also, it has other applications. What has happened? It can also be useful in the destruction of kidney stones by acoustic intensity in the order of 1000 to 10,000 watt per centimeter square by ultrasound, which is sufficiently high so that cavitation generally happens. Useful in ultrasonic cleaning devices in improving the performance of the torpedoes. So degree of cavitation can be expressed by this equation. Kd in this equation is called the degree of cavitation or the cavitation number. When Kd is small, cavitation is likely to develop. Okay. Kv is small means this pressure difference is small and the kinetic energy is very high. Cavitation occurs if Kd is less than the critical cavitation number, which depends on the geometry and the Reynolds number. So there are some examples: typical Ranel lift coefficient and critical cavitation numbers for hydrofoil. Okay. The drag coefficient as a function of degree of cavitation can be defined like CD equals to CD at 0. Drag coefficient at certain cavitation, drag coefficient without cavitation plus the cavitation 1 plus cavitation number. So this is a drag coefficient without cavitation at R equals to 10 to the power 5. So this problem. Okay, I think we have understood it. Now I will show some derivation that how these expressions are coming, from where these expressions are coming. So I'll go very fast. So we have seen that, so this is the lift pressure. So there is a particle and the flow is coming from here. If we are considering this area, so this area, that dA, this is the area direction. Okay. So this is the area direction. This is the P direction. That is, the pressure is working in this way and the stress is working in this way. So so total force will be, if you consider dF, total force at this small area, so it will consider the pressure force, that means the perpendicular force, and it will consider the shear force, right? So this shear force, perpendicular force is minus PdA, because pressure is acting in the opposite direction, right? And here it is tau W dA. So both of them have component in the along with the flow and in perpendicular to the flow. So depending on that, pressure drag, pressure lift, and friction drag, friction lift are coming. Okay, so this is total pressure is then nothing but the tau W dA, integration of tau W dA minus PD. Okay, so this is the concept. So this is the parallel portion. This is the parallel portion, and this is the perpendicular. So perpendicular. Sorry. Yes. So this is here called in the direction of relative velocity, that is drag, and this is the lift. Okay. And each component has pressure drag and shear drag, and this has pressure lift and shear lift. Okay. Now how this is coming? The expression of drag force. So from the experiment, we have seen that from the experiment, people have, like earlier scientists have understood that the drag force on a solid object, drag force on a solid object, we can say that experiments suggest that drag force on a solid object depends on the velocity, right? That is u, velocity of the fluid. So if you have seen so far, right, you have seen that this is the drag, like we are talking about. So it will definitely, we have seen in the lecture notes that how this flow velocity is depending, right? How That flow velocity will tell you about the how the eddies, how the chaotic motion will create. So it is definitely depend on the velocity of the fluid. Then it also depend on the density of the fluid, because the pattern will not be same for in case of water, in case of oil, or in case of honey, right? Similar, it will also depend on the viscosity, which is true. Also, it is depend on the size. So it is the diameter, equivalent diameter, right? So now, if you take a sphere, or leave it. So now, how can I define in pi theorem, Buckingham pi theorem? So Fd becomes a function of velocity, density, viscosity, and projection diameter or particulate diameter. So now n is 5, right? And m is 3. So pi number will be 2. So there will be two differential numbers. So how can we rewrite this? So now you can write Fd by rho u square dp square equals to phi of u rho. U is the mean free velocity, so u rho dp by mu. You can combine this, right? So you know this is the R E P. This is the Reynolds number. So this is definition is particulate Reynolds number. So because dp is varying for different shape of particles. So this is the particulate Reynolds number. Now what is coming? So now you can write that Fd, now you know that Fd can be write half rho u square dp square, and it is a function of, now it has function of REP, particulate Reynolds number, right? And now this Fd becomes half psi of rho u square dp square. So this term can be called as drag coefficient, and the expression is CD rho u square dp square. So this CD is the drag coefficient, right? So now you can understand that from Buckingham pi theorem, we are calculating this. So what will be this drag coefficient or friction coefficient? Drag coefficient over a laminar flow, over a plate. So drag coefficient for a flow over a flat plate, laminar one. So if you draw the diagram, so flow is coming over this flat plate and we are calculating drag coefficient in this region. So it is the length is L, This is B, width is B, and this is x direction, this is dx direction. And drag coefficient is happening and the perpendicular along the flow, right? So it will be tau w, this is the shear stress part, and b dx, right? So we are considering laminar flow regime, right? So CD, we know that CD drag coefficient we just calculated, right? So from there CD can be, drag coefficient is CD equals to FD by, so from the previous case we have calculated the drag forces, from CD will be FD by half rho u square dp square. So it will be half rho u square dp square. I am calculating, but dp square means you know it is the area of the substrate. So AP is the projected area. Projected area in contact with the flow or fluid. So in case of this flat plate, the contact area is the flat plate itself. So it is the BL. It will be BL. So now if I want to write CD will be, so it will be half rho u square, AP is B into L, and FD. So FD is the drag force, right? So it will be it needs to be integrated in this now. So it will be integrated from 0 to L tau W, because there is, we are calculating the drag force, right? So it will be tau W B dx, right? So now CD will be, so tau W is constant, so tau W will come out. Or let it be. So 1 by L is there, and it is 0 to L. So tau W by half rho u square can be written together, right? You have understood this. It equals to dx. So it is the friction factor in the case we have seen previous. So now what is coming? So this term we can write it together, 0 to L. This is CF dx. So this term we have seen earlier. This term is represented as the friction factor, right? When we are calculating the friction factor, drag friction coefficient expression earlier inside the fluid flow, this term came there, right? This is the friction factor, scale friction factor or coefficient, whatever it is. So now you know the earlier case you have learned that for laminar flow, CF expression 0.664 divided by root under Reynolds number for that particular area, right? So CD will be 1 by L 0 to L, expression 0.664. So you can now expand this x, which is x u by mu, right? Mu means rho by mu. So it is mu by rho. Mu is mu by rho, right? So here it is written as rho by mu, so it is in the denominator dx. Now, if you just integrate it, CD will be 1 by L is always there, and this term is constant 0.664 by U by nu to the power half, and that is x to the power minus half plus 1, that means half by minus half plus 1 is half. So it will be 0 to integrated over 0 to L. So what it is coming? It's coming as 2 into 0.664. That is 1.328. Sorry, 8 divided by L, and there is U by U to the power half, and it will be L to the power half, right? So what it will be there? So it is 1.328 by UL by nu to the power half. So it can be represented as 1.328 divided by root under REL. For this, REL is written for the flow over a flat plate, right? Now, drag coefficient for a drag coefficient So now for the drag coefficient for flow over a flat plate in turbulent region, in case of turbulent flow basically. So what is coming? So we'll do the previous derivation similarly. So in case of, so this both the steps will be same. So here in this case CF will be changed for turbulent flow. So here the CF is for turbulent region, the spin friction factor is 0.0594 divided by Rex to the power 1 by 5, right? Now if you do the integration, CD equals to 1 by L, 0 to L, 0.0594 by Rex was XU by mu to the power 1 by 5 into dx, right? So it will be 1 by L into 0.0594 by U by nu is U and nu both are constants, so it will be U by nu to the power 1/5. So it is x to the power minus 1 by 5 dx, right? So it will be minus 1 by 5 plus 1 divided by minus 1 by 5 plus 1 from 0 to L. So it is CD equals to 0.0594 divided by L U by nu to the power 1 by 5. So it is 1 minus 1 by 5 means 4 by 5. So it is x to the power 4 by 5 by 4 by 5 from 0 to L. So now what it is coming, CD is so if you multiply this with 5 by 4, so it is almost coming 0.075 divided by L U nu to the power 1 by 5 into it will be L to the power 4 by 5. If you replace this, it will be L to the power 4 by 5. And now it will coming as 0.075 U L to the power nu to the power 1 by 5. If you calculate, you will get it. So finally it will be 0.075 by REL to the power 1 by 5. So previously for laminar flow case, it was 1.328 by root under REL, that is REL to the power half. For turbulent case, it is 0.075 divided by REL to the power 1 by 5. Okay. Next, just we will discuss the where the separation happens with image. So suppose there is a particle, right? Spherical particle. And Reynolds number is high. Not much high. Please just greater than 1. So what will happen? So flow is going like this. Flow is like this way, excuse me, this way, and this point is the stagnation point, right? So suppose this is the half and the flow separation has started from this portion, right? From this. Here the boundary layer effect is there, so it is the here it is the shear drag. Here the drag force is applied and the flow separation is happening at this portion, from this portion, right? So this angle is almost 80 or 85 degrees. And in this portion, the fluid started forming eddies. So pressure here. So when the fluid starts forming eddies, the fluid becomes chaotic and that leads to pressure drop. So here in the wake region pressure is PW at the outer region pressure is suppose P, so PW will always be less than P, right? So this is the wake region. It is called wake region. This wake region contribute to pressure drag. Contribute to pressure drag. So when RE is 50, you have gone through these things in the notes. So again, I am doing RE is greater than 50. Vortex disengagement starts. And beyond that, for RE equals to greater than 90, it follows a regular pattern. It follows a regular pattern. Okay. So now what is happening? So fluid is coming like this, obviously, from the both side. And what is happening? This fluid here, this portion fluid is started because now RE is again increased, right? So this will come alternately, and this is called the vortex disengagement. So you can, they are not coming together, but they are in the opposite, equally opposite, and they are coming in alternate position. See, like this. So this is called von Karman vortex street, right? Now, when the vortex disengage, when the vortex disengages and there is a pressure pulsation, that means pressure is fluctuating, pressure is continuously fluctuating in this region because vortex disengagement starts here, right? Pressure pulsation is happening. There is a pressure pulsations in the wake region, right? Because pressure fluctuations will happen. And due to this pressure fluctuation or pressure pulsation, then a vibration is generated, and this vibration frequency after some time will be same as vortex shading frequency. Okay. So now what we'll see that there is a sudden drop. Now what we'll see, now I'm writing this because this is very important. So this is very important to understand the physics. So now there is a sudden, you can go through this and understand by your own with the example I have given, with the or the in the note also it is given. There is a sudden drop in the drag coefficient versus RE profile at 3 into 10 to the power 5 because the wake region starts shrinking, because the wake region starts shrinking abruptly and a small portion comes under pressure drag and rest of the region is pressure drag and rest of the region is under shear drag. So now what happens if I draw this, when this, so now this is becomes this wake region shrinks. Okay, this wake region shrinks down and now this position, the separation starts at this angle. Okay, the flow separation start at this angle, so it is now around 140 degree or on 30 degree. So now this position, this position remains under the pressure drag and this position remains under shear drag. So earlier this much position was under shear drag and small portion and this where the flow separation was starting, right? Now the situation has been reversed. Okay, so if the point of separation, what you will understand that if the point of separation means flow separation can be pushed to the rear half of the object, then the pressure drag as well as the overall drag can be reduced. Overall drag can be reduced. Okay, so why? Because in the earlier case you have seen that flow separation happens at 85 degree angle. So from here only the flow separation happens and it leads to chaotic region or eddies, von Karman vortex disengagement. And if This flow separations can be shifted from this the rear portion of the object or more than 90-degree situation, the overall pressure drag will be reduced, right? So we have to reduce the pressure drag basically to keep it more streamlined. So we have to make our object like this, more streamlined. So due to that, this particle, or due to reduce to reduce this effect of wake, we start making the like this shape of wings, or you can compare it with the aeroplane shape, right? This is called streamline. Now you can see this pressure drag is at this point and whole region is under shear drag. So fluid is going like this. Okay. So here the point A is there, and here this is point B. So here the pressure is PA and VA. Here there is PB and VB equals to 0, because this is a stagnation point. Earlier I told. So here the just fluid streamline, the whatever fluid is coming at this point, it just stops there, right? So this is the stagnation point. So what is there? So at B point, B will experience highest pressure because the single streamline is getting recoiled from the point. And this is called stagnation point. And this is called stagnation point. So if you compare it with T by C and force, so what is T by C? T by C is, this is the T by C you have, if you remember sir's note, it is for the aerofoil, it is the thickness and it is the chord length, right? So this is T, this is L. So this will go like this, shear drag, and pressure, shear drag will go like this, pressure drag will go like this, right? So with the distance. So this is the total drag. This is the total drag, right? And at this point between A and B, if you apply your Bernoulli's equation, what will come? It will be like PA by rho plus VA square by 2 equals to you can write G, you cannot write G. The unit will be different, but it is the same. And equals to PB by rho, right? Because VB is 0 literally here. So at this point, PB will be PA plus half rho VA square. So this PB is the stagnation pressure, which is the highest one at this zone. PA is the static pressure, and this is the dynamic pressure. Okay, I think now it is more clear. Now let's do the assignment first. Drag force is directly proportional to area, mass density, density of fluid, flow speed. So we know drag force is FD is CD half rho U square by AP. So drag free and AP is the projected area, not the whole, total area. So we can area will not be there, mass density is not the density of the fluid and flow speed square, right? So it is the density of the fluid. So twin vortices form due to drag for a cylindrical body in case of a viscous fluid when the Reynolds number is, as per the lecture, it is the between 40 to 70, right? So this is, so the vortex is forming like this, and this vortex is forming like this, right? Next, bodies with a larger cross section will have lower drag, higher drag, same drag, and no drag. So larger cross sectional area, that means like this. So the cross sectional area is higher than this, or you can complete think of like this. So here the cross sectional area is much more higher than this portion, right? So it will lead to higher drag. Because here the pressure drag is high than the shear drag. If the pressure drag is high, the overall drag will be high. Next, what is the dimension of the drag coefficient? So you can calculate. So FD equals to half CD rho U square, and this is AP, right? So this is the drag force. Force is always Newton. And this is CD, we don't know. Rho is kg per meter cube. This is meter square, second square. AP is meter square. Right? So it will be 1 meter will be left here. So kg meter per second square. So N is itself kg meter per second square, you know, mass into acceleration. So it is also N. So CD becomes 1. So it is dimensionless number. Next. For a streamlined body to achieve a low drag coefficient, the boundary layer must flow over the body, be attached to the body, move away from the body, move parallel to the body. So we have seen that for a streamlined body is like this, right? So the boundary layer for low drag coefficient, boundary layer must be attached to the body as long as possible, okay? Because this will lead to reduced pressure drag. Next, to reduce the drag, it suffices to make a body into a shape from which the flow does not separate. The shape is spherical shape, streamlined shape, cylindrical shape. So for spherical shape, it will the higher drag and the pressure drag and the stress drag will be similar. For streamlined, the pressure drag will be low. For cylinder, also pressure drag will be higher. So it is the streamlined drag. We have to reduce the pressure drag. That is the main goal. Next, according to the Stokes equation, the drag coefficient. So if we want to calculate, so CD was FD by half rho U square pi by 4 dp square, right, for a sphere. I'm telling. And FD for a sphere, we know that it is nothing but 3 pi mu dp into U, right? So if you put this 3 pi mu dpu by, it becomes pi by 8 rho U square dp square, right? So pi by will be cancelled out. 1 U will be cancelled out. 1 dp will be cancelled out, right? So it will be 3 into 8 will be 24. And now we can there is a rho, there is U, and there is 1 dp, and you can bring the mu from top to bottom here. So it will be nothing but your 25 by R, Reynolds number, right? So it is 24 by R. Next. Stokes equation for a sphere is valid in the Reynolds number range of less than 0.1. So it is 0.2 to 5. So RE has to be less than 1. Drag force on a sphere is not proportional to, so drag force on a sphere is not proportional to U square A 1 by rho or rho. It is obviously 1 by rho. It is proportional to rho. Next, for a flow in between this around a sphere, select the correct option for the drag force of the modified Stokes equation by Osin, where U is the relative velocity. Yeah. So it is option 24 by Ri1 plus 3 by 16 Re A rho U square. So CD is this. So CD drag coefficient changes from 24 by Re to 24 by Re plus 1 plus 3 by 16 Re. Okay, so it is this. Next, cavitation is a process of, so in cavitation what happens? In the low pressure area, bubble forms, right? So it is the vapor formation. Bubble means vapor. It means inside there is air and outside there is liquid. Am I saying it right? Let me check. A sphere of gas in liquid. Okay. So inside there is gas, or here in case it is air, and it is outside there is liquid. This is bubble. And what is droplet? Droplet is liquid inside and air outside. Okay. So this is droplet. Next, pressure lift is generally the integration or differentiation or multiplication or subtraction over the whole body surface of the component in the direction normal of the flow velocity. The pressure lift is the integration. Next, a successful spinner always tries to follow Kutta-Joukowski equation, right? The expression was where the fluid, in the fluid, the particle or the object itself is rotating. So from the Bernoulli's equation, there is an expression, right? So that is the Kutta-Joukowski's equation. That number is a ratio of flow velocity past a boundary to the local speed of the sound. Option A. Next, due to cavitation phenomena, the life of blade decreases because as due to cavitation the bubble creates, and in the low pressure zone the bubble creates, and when this bubble reaches to the high pressure area they just burst, and this bursting leads to high vibration, and that vibration erodes the surface of the blades. Okay, so this is the decreases. This will be decreased answer. The lift coefficient reaches 0 at a certain angle of attack alpha, right? Which is called the zero lift angle. As the angle of attack increases from the zero lift angle, the lift coefficient increases. So in the aerofoil expression we have seen this. The cavities grow further. Liquid pressure, if liquid pressure and flow velocity are low, liquid pressure and flow velocity are high, liquid pressure is large and flow velocity is low, liquid pressure is low and the flow velocity is large. So cavity will go when the pressure is low and velocity is large. Option D. Next. Generally, the body of the wing or blade is manufactured such that the lift and drag become equal. No, when the body lift and drag are equal, that means it is in the case of sphere. That will lead to more chaotic motion, more wakes or more vortexes, right? So lift should be greater than the drag, and that leads to this kind of streamlined structure. So it is false. Next, why a wing produces lift? A circular flow is produced. Trailing edges are sharpened. So here you can see about the wing, that here a circular flow started because of this edge are sharpened here in this region. Here from here the flow separation will happen, right? And here there is edge. This because of this sharpening there the wake will come. A wing moves from a stationary state initially. Yes. So the reason is all of that. The degree of cavitation depends on the density of fluid, velocity, vapor pressure, all of the above. So it is also the answer, all of the above. Because cavitation will depend on the density of the fluid, right? Because it is also dependent on the drag or speed of the fluid. So in general, it will be density above and vapor pressure. Density, velocity, and vapor pressure, all of them. So the right answer you can correct is all of them. Okay. So we'll do some more equations, also some more problems. So at which angle of attack does the stall phenomena typically occur for the aerofoil section discussed, and what its primary physical cause? So the stall phenomena occurs when, in the case of aerofoil, so if the aerofoil angle, this is the aerofoil angle alpha, if it reaches very high, so the flow will separate from this point. Flow will separate from this point. Okay. And it will create a chaotic motion at the bottom. So at 0 degree, what happens? The pressure on the upper and lower surfaces equalizes. At 12 degree, the momentum coefficient reaches its minimum value. At 16 degree, the flow separates from the upper surface of the wing. At 20 degree, the drag coefficient becomes lower than the lift coefficient. So it is the option C. So at 16 degree, the flow separates. Next, according to D'Alembert's paradox, what is the theoretical drag force on a cylinder placed in a non-viscous fluid? It is equal to the kinetic energy of the fluid. It is zero as the integrated pressure distribution turns out to be zero. It is proportional to the square of the cylinder's radius. It is determined solely by the stagnation point pressure. So non-viscous fluid means Non-viscous fluid means ideal fluid, basically. So in case of ideal fluid, the viscosity viscosity is not present. So it will lead to a, for cylinder, it will lead to non-viscous fluid. So it will lead to a equal pressure distribution at both sides. So equal pressure distribution at both sides, which lead to net pressure difference. It will be zero. As the integrated pressure distribution turns out to be zero. So net pressure will be zero. Under what condition does supercavitation occur, leading to a stabilization of flow and reduction in noise? When the local pressure is exactly equal to the saturation pressure, when the cavity grows beyond twice the chord length of the aerofoil, when the fluid temperature exceeds 100 degrees centigrade, when the cavitation number reaches its maximum critical value. So it is option B. When the cavity grows beyond twice the chord length of the aerofoil. Okay, so chord length is this. So when the vapor cavity becomes large enough to extend beyond the object. So here the vapor cavity becomes large enough beyond the extent of the object. Specifically, when the cavity grows beyond twice the chord length, the flow stabilizes, leading to significant reduction in the noise and vibration typically associated with standard cavitation. Now we'll do some problems. So a 2 mm diameter wire stands erect in air. So 2 mm diameter wire. Okay. Erect stands erect बोला है. So it is erect. It is vertically present in air. The fluid is air. It starts vibrating as air flows past it at a velocity of 90 km per hour. If the kinematic viscosity of the air is 0.15 Stokes, calculate the number of vortices separating from the wire every second. So we'll do the problem in centimeter. Okay, you can do it. So D is given, V is given. Okay, so D is 0.2 centimeter. This U is 90 kilometer per hour. That means 90 into kilometer means meter centimeter, right? So it will be 10 to the power 5 hour. This is 3600. So it will come in as a 2500 centimeter per second. Then kinematic viscosity is Stokes. 0.15 Stokes means 0.15 centimeter square per second. So now if we calculate the Reynolds number. Reynolds number is U d by nu. So d will be important because this flow is crossing the diameter of the wire. So U is 2500, d is 0.2 and nu is 0.15. It is coming as 3333.3. So now we can calculate from the equation that is given in the first PDF, where you can calculate the number of vortices per second. So formula was n equals to 0.198 U by D 1 minus 19.7 by RE. So put the values and you will get it. So it will be 19.7 by 3333.3, 1 minus this into 2500 into 0.198 divided by D is the diameter, so it is small d, sorry. So it is small d is 0.2. So it is coming as 2460 cycles per second. This is the answer. Next, a hydrofoil with a chord length of 40 centimeter operates 30 centimeter below the water surface. Okay. At a speed of 16 meter per second, the critical cavitation number of this hydrofoil's angle of attack is 1.2. Determine if cavitation will occur or not. So it is there is water, and below the 30 centimeter there is the airfoil. Okay. Now we'll calculate the upstream pressure, that is P infinite, which is rho GH plus P atmospheric pressure. So it will be rho is given, GH is 30 centimeter, right? So 9.81 into 1000 into 0.330 centimeter is given, right? So it is 0.3 meter, and plus 10 to the power 5 Pascal. It is coming as 102943. 102943 Pascal, the upstream pressure. Okay. And to calculate the cavitation number KD, we have to know the upstream pressure minus the speed total surface at below, what is vapor pressure V divided by half rho dynamic pressure. So it will be, vapor pressure is given as 1600 divided by 5000 by U square. U is 16 square. It is coming as 0.79. So critical cavitation number is given as 1.2, right? So 0.79 is less than 1.2. That means the cavitation will occur, because it beyond critical cavitation, the cavitation will not occur. Okay. So it is less than the cavitation will occur. So we'll have to make the device, or keep the distance of the device in such a way so that it will greater than the value, critical value 1.2. Okay. Next, an object is placed in an air stream with a uniform free velocity and a free stream pressure. Calculate the pressure at the stagnation point on the body surface. So simply you can calculate it with the Bernoulli's expression. So from where it is coming, we have derived that stagnation point at PB is coming as the free stream velocity PA plus rho V square by 2 or U square by 2. So if you put all the values, because all the values are given, so it will be free stream pressure is 101,325. So it is coming as 101,876.25 Pascal. This is the stagnation pressure. Next. A flat plate is 2 meter wide and 4 meter long. Water flows parallel to its length. Calculate total drag force on one side. So 2 meter wide and 4 meter long. Slow fluid passing is like this. So water flows parallel to its length. Okay. Sorry, I have drawn incorrectly. So this is the plate. This is 4 meter, this is 2 meter, and fluid is passing like this. Calculate the total drag force on one side of the plate if the boundary layer is assumed to be turbulent over the entire surface. So for boundary, we have calculated. So it is 0.074 or 0.075, whatever you can take. Okay. Because it is coming close in between 0.074 and 0.075. Okay. So you can take any of them. So for turbulent flow, we have derived that coefficient factor is 0.074 divided by REL to the power minus I. So RE will be U, that is 2 meter, U, L is here the 4, and nu is 10 to the power minus 6, right? So it is coming as 0.074 0.074 by 8 into 10 to the power 6. Okay, sorry, I have missed this. So it is 1 RDL to the power 1 by 5, right? So it will be 8 into 10 to the power 6 to the power 1 by 5, and that will be 0.074 by n. This will be 3.08 into 10 to the power minus 3, right? This is your CF. Now you can calculate the drag force. FD equals to half CF, a projected area, rho U square. Projected area is just 4 into 2. That is the length into width. Okay, so if you put the values, you will get so already I have written that 2, say here you don't need to write. It is coming as 49.28 Newton. Okay, this is the answer. Next, a cylinder with a radius of 15 centimeter is rotating in a uniform air stream where the free stream velocity is 20 meter per second. The air density is 1.2 kg per meter cube. If the cylinder's rotation creates a circular velocity u of 5 centimeter per second at its surface, calculate the circulation tau and the lift force. So, circulation tau expression was 2 pi r naught into u. So, from there it will be 203.14 into r naught is your 15 centimeter radius, that is 0.15 into small u is 5, that is coming as 4.71 meter square per second. So this is the circulation, and lift force L is defined as rho capital free stream velocity into circulation. So it is 1.2 into 4.71 into free velocity is 20. So it is 113.04 Newton per meter. Okay. The last question for this section is calculate the drag force on a sphere of diameter 1 centimeter moving through an oil bath at 0.5 meter per second. The oil has a density and a dynamic viscosity. Because Reynolds number is slightly above the Stokes range, use Oseen's modification to find the drag. So Oseen's modification will be CD equals to 24 by RE into 1 plus 3 by 16 into RE, right? So first we'll calculate the RE, then we will be coming. So RE is your rho UD by mu. So rho is 900 for oil, U is given as 0.5, D is 0.01 and mu is 0.045. So RE is coming as perfect 100. So now CD will be into 3 by 16 plus 1 into 24 by 100, that is 4.74. So this is your drag, and drag force will be FD equals to half rho CD U square into AP. So AP projected area will be a sphere, so that will be pi by 4 d square. Okay, so here AP is pi by 4 d square. So AP is coming as 7.85 into 10 to the power minus 5 meter square. Okay, so now if you multiply into 0.5 square into 4.74 into rho is 900 divided by 2. So it is coming as 0.0418. 0.04186 Newton. Okay, so this is your answer. So that is for today's session. I hope you have understood what is drag, what is lift, what is cavitation, and how the wake region forms around around an obstruction. How and to negate this, to remove this, how the shape of the object has to be changed. It should be more streamlined. That is why our airplane and um, the wings are like that, more streamlined to create minimum wake. Okay. So please go through this. I'll be uploading this lecture today night. So if you miss something, please go through that. Go to the lecture, and we'll meet on next week. So till then, goodbye.